Have you ever gazed up at the stars and felt a sense of timelessness? The universe has been around for nearly 14 billion years. Planets form, stars are born, stars die. Galaxies collide in a slow cosmic dance. In the face of all that, our own lifespan feels so brief, a fleeting moment. But what if it didn't have to be? What if the same laws of chemistry and physics that govern the cosmos could be used to extend our own time? What if we could pause or even rewind our biological clock? The quest for immortality isn't just a myth, it's a scientific frontier, a journey into the very essence of what it means to be alive. To understand how we might live longer, we must first understand why we grow old. It all begins inside our cells. Think of your body as a bustling metropolis of trillions of tiny citizens. Each citizen, each cell, carries a complete instruction manual. This manual is your DNA, a magnificent spiraling molecule, a blueprint for everything you are. Every time a cell divides to make a new one, to heal a cut or simply replace an old cell, it must copy this entire manual. It's a process of incredible fidelity, repeated billions of times over your lifetime. But the copying machine isn't perfect. At the very tips of your DNA strands are protective caps. They're called telomeres. Imagine them like the plastic tips on your shoelaces. They prevent the important parts of the DNA, the genes, from fraying with each division. But here's the catch. With every single copy, these telomeres get a little bit shorter. Eventually, after many divisions, the telomeres become too short to protect the DNA anymore. The cell can no longer divide safely. It enters a state of retirement, a kind of cellular old age. This process is happening in you right now. This shortening of telomeres is one of the fundamental pacemakers of aging. Beyond the ticking clock of telomeres, another drama unfolds within each of your cells. Your cells are power plants, constantly burning fuel to generate energy. This process, called metabolism, is essential for life. It powers your every thought, your every movement, your every heartbeat. But this energy production has a byproduct, a kind of cellular exhaust. These byproducts are highly reactive molecules known as free radicals. They are thieves, hungry for electrons, and they will steal them from any molecule they encounter. Think of it like rust. When iron is exposed to oxygen, it oxidizes, it rusts, weakens, and falls apart. A similar process happens inside you. Free radicals are like tiny molecular bullies roaming through your cells and causing oxidative stress. They can damage proteins, lipids, and your DNA instruction manual. But the story doesn't end there. Our cells are not defenseless. They have evolved a sophisticated security force made up of antioxidants. These are heroic molecules that can donate an electron to a free radical without becoming unstable themselves. Your body produces some of its own antioxidants, and you get many more from fruits and vegetables. It's a beautiful, elegant system of balance, a perpetual push and pull. This internal warfare between free radicals and antioxidants is a key theater in the science of aging. So what happens when a cell's telomeres get too short or it suffers too much DNA damage? It stops dividing, it enters that state of retirement we talked about. This is called cellular senescence. In a young, healthy body, this is a good thing. The immune system then acts like a cleanup crew, identifying these retired senescent cells and clearing them away. However, as we age, two things happen. First, the number of these senescent cells increases dramatically. Second, our immune system becomes less efficient at its cleanup job. These senescent cells secrete a cocktail of inflammatory chemicals that can harm healthy neighboring cells. This is where a new and exciting field of chemistry comes into play. Scientists have been developing a class of drugs called senolytics. These drugs are designed to be molecular assassins. They can selectively seek out and destroy these lingering senescent cells. The goal is to reboot the body's natural cleanup process. The research is still in its early stages, but the results in animal studies have been remarkable. Mice treated with senolytic drugs have shown improvements in cardiovascular function, are more physically active, and even have healthier fur. The effect is like a deep cleaning at the cellular level. It's not a fountain of youth, but a restoration. A way of turning back the clock not by stopping time, but by tidying up the damage that time has left behind. Clearing out old cells is one thing. But what about repairing the intricate damage that has already been done? This is where chemistry points toward molecular machinery. Imagine deploying fleets of microscopic robots into our bloodstream. Programmable devices no larger than a blood cell, designed atom by atom to perform specific tasks. A 24/7 internal repair crew patrolling arteries, identifying cancer cells, and performing precise genetic repairs. This isn't science fiction, it's active research, chemistry, engineering, and medicine converging. Beyond bots, synthetic biology. Designing entirely new molecules that don't exist in nature. Permanent, super-efficient antioxidants. Synthetic enzymes clearing molecular garbage, artificial red blood cells carrying oxygen more efficiently, synthetic immune cells with perfect memory. The promise, not just slowing aging, but reversing it. Becoming architects of our own biology, from passive observers to active managers of molecular health. The science is tantalizing. The chemistry is powerful. We stand on the precipice of a world where we might conquer aging, our oldest and most relentless foe. A world where a lifespan of 150 years, 500 years, 1,000 years might be possible. We could have lifetimes to learn multiple disciplines, to travel to other planets, to watch civilizations rise and fall. It's a breathtaking prospect. But with this immense power comes an equally immense responsibility. We must ask ourselves the hard questions. If we could live for centuries, should we? Who would get access to these life-extending therapies? Would they be available to everyone, or only to the wealthy? How would our planet, already straining under 8 billion people, sustain a population that never leaves? We would have to completely rethink everything. Family, career, inheritance, and the very meaning of human life. Would a life without end lose its preciousness? Does the knowledge that our time is finite give our choices meaning, our relationships urgency, and our achievements value? The chemistry can tell us how, but it can never tell us if we should. The universe has given us the tools to understand ourselves. The prospect of radical life extension forces us to ask the ultimate question. What does it mean to be human? The cosmos awaits our decision.